The next speaker will speak about Python data structure implementation, about list and dict. It's Flavien. Please welcome Fabien.
Can everyone hear me? Cool. Well, hi everyone. Thanks for being here. It's quite impressive, actually. So today I'm going to talk about like data structures in Python and how CPython implements lists and dictionaries. So, well, before we get started, I'm a software engineer working for Yelp. It's a company that connects people with great local businesses. So first, if you take a look at this tiny, bad, and actually not real-life owl example, you can see that whether we want to add an item to a list that has like 0 element, 1 element, 1,000 elements, the time it takes to add a new element is quite constant. The same goes for dictionaries, so we'll focus on like how CPython does that. We're going to focus on CPython 3.6. That's the last version as of today. Like lists and dictionaries are quite used a lot, but they seem pretty easy to use. But actually, they have like lots of hidden and really cool ideas behind them. So we'll try to like dig into them today. They're made up of lots of lines of code and lots of comments. So like, if you want to know more about them, at the end of this presentation, you can just like go to the Python website and look at the code. It's really well commented, and it's really sometimes very good written. And so let's get started with lists. A list basically is a sequence of values. In Python is objects, indexed starting from 0. Sorry. They provide constant time insertion, random access, and linear time deletion. And so how does CPython does that? Internally, they use something called a vector, which is an over-allocated array. So even though your list may have, like, say, 5 items, it's possible that it has space for, like, say, 8 items, actually. And so the invariant that the vector must, like, comply to is that the actual length of the list has to be, like, lower or equal than the actual capacity. So a few ways to create a list, like, I'm sure like most of you know about all of them. When you create an empty list, its size is 0 and the capacity of the vector is also 0. When you create a list, like say 0, 1, 2, 3, 4, and you know like the size, when you like declare it, the size will be like 5 and the capacity will also be 5. So now let's play with some like theory examples. So let's say like during your free time you want to help connect people with great local businesses. You want like put these businesses into categories. So let's create a new empty list of categories and add a new category to it. So you're using like the append method. So what's really happening is that we have an empty list. Whenever we want to append something, we call a function that's called resize with like the current size of the list, sorry, plus 1. And after that, we set the last value to be like food for this example. So what resize does is it takes as input a new size, checks whether the new size falls between like half of the capacity and the capacity itself, so to make sure we like comply to the invariant. If that's the case, we just do nothing. We have enough space to add the new item, so we just like say, okay, you can go on. But if we don't, like this condition isn't met, we need to compute a new capacity of the list. And so the pattern that this capacity follows is like this one. So new size over it plus the new size plus like some rest. And then once we have the new capacity, we call like realloc to like, well, reallocate the list with the new capacity. And so this capacity patterns might seem quite weird. So like this follows this like 0, 4, 8, 16, etc. But what we can see is that because of the like new size over 8, the growth rate is about like 12.5%, like when the list grows beyond like a certain amount of items. And so this like 12.5% is like trade-off between space and time. Like we want to have constant time on like insertion on average, but we also want to like not waste too much memory. So like that's just trade-off that has been made by CPython developers like that seems to work. One thing to note about append, and like let's say you want to like create a list with like when you know like its content when you declare it, its size would be 5 for this one and its capacity would be 5. If instead you decide to like create an empty list and call append, then append, due to the gross pattern, the size would also be 5, but the capacity would be 8. So even though those two lists contain the same items, they're not the same and they don't have the same memory footprint. Now, what if you want to remove an item from a list? So let's say you have like this 4 items in your list and you want to remove them. One of the ways to do it is to call the pop method. You can give it an index, which is going to be like the index of the item we want to remove. There are 2 cases. The first one, if it's like you want to remove the last item in the list, and the other one is if you want to remove like an item that's not the last one. So if you want to remove the last one, it is pretty easy. You just like call the resize function that we mentioned before, and we've given it like the size -1, and so like it's gonna take care of reallocating if you have to. But sorry. But if we don't want to remove like the last index, like the last item, we'll have to move all the items like after the item we want to remove. We'll shift them like 1 slot to the left. What's really happening is that you could like use like slicing to do it. It's exactly the same thing. And what happens under the hood is that a call to mem_move is done, which just copies memory from a chunk of memory from source to destination, and then calls resize with the sign -1. So let's go with an example. So we have this list and we want to remove tacos. Who want to do that anyway? So so we have size equals 4, capacity equals 4. We pop the item at the index 1. First, we're going to call mem_move. It's going to shift like bar and dentist 1 to the left. It's going to look like this. But now we have like 2 dentists and the size is still 4 and the capacity is still 4. So what happens next is like they're called to resize. So resize is going to take care of removing the last entry, so dentist. Now we don't have dentist anymore, the size is 3. 3 is between 2 and 4, so the invariant is respected, and so we can just like finish and like the list has size 3 and has room for one more like item in the future. A couple of miscellaneous about list. If you want to use the list as a queue, don't. Like using append to enqueue and pop 0 to dequeue. CPython has a collection called a deck that does exactly what you want with constant time insertion and deletion. Second is that slicing is really powerful. I won't get into the details, but like these are some of the things you can do with it. It's pretty powerful, and almost nobody uses that, so maybe that's kind of useless. But and next is like reference reuse scheme. So whenever you create a new list, you need to create a new reference to it, and whenever you delete a list, you need to delete its reference. This is on using malloc and free. Calling malloc and free takes some amount of time. So to speed this up, CPython has like a list of free references that have been already created. So whenever you delete a list, you don't remove the reference, you keep it, and if you want to create another list, you're going to reuse this reference. So here you can see that B and D have the same reference. That's because D reused B's reference. And this works for up to 80 references. After that, it's just the normal like malloc free flow. So that's it for the list. Now let's move on to dictionaries. So dictionaries are meant to store key value pairs. Here are some ways to like create new dictionaries. So the use cases of dictionaries, like there are quite a lot of them, and maybe like you won't think about all of them. So the first one is keyword arguments. So each like when you pass keyword argument to a function or method, each key gets written about once and read about once. Next is class methods. They are also stored in the dictionary. Attributes and global variables. Built-ins. When you want to do uniquification, so remove duplicates from a list, for instance, or like count things. And any other use, so you want like to do whatever you want. You want to write keys to read them, and you can sometimes have deletions too. So a bit of history about dictionaries. So implementation changed quite a lot over time. 3.6 has a shiny new implementation that's inspired from the implementation of PyPy's dictionaries. They are ordered, so you can have the whenever you want to call like keys, values, or items, you have them in the order of which you have inserted them. They're also memory efficient. They're try to reuse keys when possible. I won't have time to get into much of the details, but there's a PEP for it. And so they introduced like split tables and combined tables. For today, I'm going to focus on combined tables, but they share pretty much like they have a lot of things in common. So what do they give us? Average constant time insertion, lookup, and deletion. So everything's super fast. Like how can you do that? Like using arrays. And so we have keys, like dictionaries have keys that are Python objects. Arrays have indices that are like integers. So we need to find a way to transform objects to integers, and that's where hashing comes in handy. So basically, a hash function is a function that's used to map data from arbitrary size to data of almost fixed size. So in Python, the data from arbitrary size is an object, and data from fixed size is like a 32 or 64-bit integer. Depends on the architecture. We'll suppose like today it's going to be 64 integers. So we could talk about hash like for hours. So just like almost all non-mutable objects in Python can be hashed. There's a hash built-in that gives you the hash of an object, and basically it's like an integer. And like if you want to hash 42, this gives you an integer that's represented here as a bit string. So it's just like zeros and ones, like 64 zeros or ones. Same like with 1.61, this gives you this number, and if you want to hash like never gonna give, this gives you this other number. Like you don't have to know how hash functions work deeply to like just use them. One thing to note about hash functions is that like the input space is of arbitrary size and the output space is fixed, so there might be collisions. The easiest one is like -1 and -2 have the same hash in Python, in CPython. And so having the same hash doesn't mean you have to be the same value. Another thing to note is that similar values often have dissimilar hashes. So if you want to like speak English and say hello, the hash is going to be like this number. But if you now want to speak German and say hallo, the hash is completely different, even though like they're pretty similar objects. And one thing you must have is like hashing the same value again and again should give you the same hash. Like hash functions that have to be deterministic. So if you want to hash hello once, twice, 1,000 times, it should give you always the same number. So now we have like a way to transform dictionary keys to hashes and then to indices of arrays. But can we actually represent dictionaries as arrays? The answer turns out to be yes. And actually in CPython 3.6, using combined tables, a dictionary is actually like 2 arrays, one array of indices and one array of entries. So let's go back to another toy example. Let's say you want to help people connect people to great local businesses, and you want to you have categories, and you want to know how many of each business you have in each category. So you create like an empty category dictionary. What happens really is that CPython creates like these 2 new tables. The first one is the table of indices, and the second one is the table of entries. Each element in the entries table is a structure containing the hash of the object. It contains the key and its value. And in the indices table, the one on the left just contains an integer like that maps to an entry in the entries table. So you can see on the left, I've represented the indices in base 10 and base 2. It's going to help us in the following slides. And so when you create an empty dictionary, the indices table that gets created as an initial size of 8. So even though your dictionary is empty, it takes some space. And so now we have our key, we want to have its index in the indices array. The indices array is of size 8 at first. So we're going to have the index in the indices table of like the key x. We hash this key, so this gives us a 64 bits number. And we take the last 3 bits of it. Why 3? It's because we have 8 entries, and to index 8 entries, we can use 3 bits for like counting from 0 to 7. And so let's like add an entry to our dictionary. So we want to have food. We hash food. This gives us this number. We take the last 3 bits, which turn out to be 000. What happens is that we add a new entry in the entries table. So we put the hash, we put the key, we put the value, and in the indices table, we go to the index 000 and say, okay, so this maps to the entry index 0. Now let's move on and add tacos and bars. Let's say like the hash of tacos, like the last 3 bits turn out to be 001, sorry. And for bar, it's going to be 101. So let's have tacos. We add a new entry. We go into the indices table, 001, this maps to the entry number 1, index 1. Now we add the third entry for bar. This, the hash is 101, so we go into the indices table. 101 is the fifth, is 5, so we go into the indices table and say, okay, so 101 maps to entry index 2, which is bar. So now let's say we want to have another category, and this, let's say dentist, and its hash turns out to be 001. What happens is that we go into the indices table, 001, we want to add dentist, but there's already something. There's already tacos, and we want to keep tacos. So we need to find a way to solve this problem. So what's happening actually is that hash collided. And so there are several methods to resolve these issues. CPython uses open addressing. And so how open addressing works is basically you have your index or your hash, and you compute a new one following a certain rule. Sorry. And so the rule used in CPython is 5 times index plus 1 modulo the size of the actual dictionary, which is 8 for us. So what's cool about this rule is that it traverses each integer in the range of 0 to size minus 1. It doesn't have to be like 0, 1, 2, 3. It can be like 4, 2, 0. As long as we see all the integers between 0 and size minus 1, we're fine. And actually, the implementation is a bit more sophisticated than just this, but like for the sake of simplicity, we can use this one. This works like really good for now. So let's go back to our example. Inserting, we have our hash colliding at 001. So in base 2 and base 10, this gives us 1. 5 times 1 plus 1 modulo 8 is 6, which in base 2 gives 110. So now we go into an indices table. 110 is free, so we can add our new entry. So everyone's happy. We have both like tacos and dentist, so we can just keep going. So now what if we want to look up in the dictionary? So like how many food items do I have? We look at the hash of food, which turns out to be 000. We go into the indices table. So 000 gives us entry index 0. So we go to the entries table, look up the index 0, and oh, we have food, so and 4,000. So that's it. Now, what if we want to know more about dentists? Like we take the hash of dentist, which is 001. We go into our indices table, 001. This maps to entry index 1. We go to entry index 1, and oh, tacos isn't dentist, so well, that's a problem. And so what it means is that the hash and the key don't match. So maybe that we just jumped before, so like hash might have collided, and so we might have ended up in another slot. So well, let's just follow the rule, and 5 times index plus 1 extra gives us 110, which maps to entry number 3, and so that's dentist. So like we're happy we have our dentist. So now, what if we want to know more about music? We don't have music in our dictionary. So how does CPython actually do that? We take a look at the hash of music, which turns out to be 000. We go into our table, 000 gives us food. Food isn't music, so well, let's just jump. Next one is 1. Tacos still isn't music, so let's keep jumping. Maybe we like jump twice, maybe more. The next one is 110, gives us dentist, still not music. Let's keep jumping. The next one is 110, and well, there's no entry related to 110, so that means that we've never seen music. So we can raise an exception, like a key error exception, and there's no music in our dictionary. Next, what if we want to delete an item from a dictionary? Let's say we want to remove tacos. Again, who would do that? But so hash is 000. Can we just say, okay, hash is 001, sorry. Let's just remove the entry index and remove the content in the entries table, and that's it. Actually, we can do this because otherwise we couldn't access dentist anymore, because if you remember, when we inserted dentist, we jumped from tacos, so if there's no tacos anymore, we can't know where dentist is located. So to solve this, what we do is, instead of removing the entry index, we just keep the entry index, remove the content in the entry, and just leave a dummy key. Dummy key is just here to say, okay, well, there used to be something here, it's not there anymore, so if you stumble upon me, just keep jumping. And so now we just can't access dentist anymore. We still can access dentist. Few caveats about the current state. 8 slot is fun, but is rarely enough. And if you want to add entries to the dictionary, your tables will be getting fuller and fuller. And so the lookups are going to be slower, and the keys make this even slower because they take an entry for basically nothing, because we deleted the item. So what we want to do is sometimes resize the dictionary. What we need to have is at least one empty slot, because otherwise we could be jumping over and over and infinitely. CPython goes even further and defines a usable fraction of the dictionary, which is 2/3 of the size. So initially, with a size of 8, we can have up to 5 entries in our dictionary. So if we take a look at the current state, we have, well, the length is 3 because we have food, bar, and dentist. The size is 8 because we can have up to 8 indices. And the usable fraction is 1 because we have 4 items in the entries. The keys take some space. So let's keep on moving and just add a new category and delete one category. This gives us this state. The length is 3, the size is 8, and the usable fraction is 0. So what if now we want to add another category? We're going to have to, we don't have space anymore, so we have to resize the dictionary. How it's done is that we have another resize function, specific to dictionaries, that take as input a minimum size. The minimum size is computed as twice the length of the current length of the dictionary plus half the current size. And so we have this minimum size that we want our dictionary to have. We compute the actual new size, which is going to be the next power of 2 of this size. Why the next power of 2? Is because we want to be able to truncate the hashes, so take the last 3 bits, the last 4 bits, the last 8 bits, etc., which turn out to be powers of 2. We create a new empty dictionary with the new size, and for each of the entries that we have in our dictionary, we just insert them in the new dictionary, and then we remove the old ones. So with our example of length 3, size 8, this gives us min size equals to 10. So the new size is going to be 16. So instead of having those last 3 bits to take the last 3 bits into account, we're going to take the last 4 bits into account. And so now we have a large array, so we can fit more items in them. We also have more free slots, so lookups and insertions is going to be faster because we won't have to jump. We're less likely to have collisions. And we don't have dummy keys anymore when we rebuild the dictionary, because if you remember, dummy keys are inserted only when we delete items from a dictionary, but now we just have a brand new dictionary, so there's no dummy keys that take space and time for nothing. On the other hand, dictionaries take more space. CPython just trades space for speed, so that's just trade-off again. Couple of miscellaneous about dictionaries. They have the same reference reuse scheme as lists, so we can save up to 80 references. And if you want to know more about split tables, I said that combined tables were made of two arrays, two arrays, like one of indices and one of entries. In split tables, we have three arrays, one of indices, one of entries, and one of values. And all the dictionaries that share the same keys have the same like indices and entries table, and they have their own values table, so that like all the keys will be in the entries table, and all the values are going to be in the values table, and so they all share like the entries table. If you want to know more about it, like the PEP 412 is like really well written and explains like everything you need to know. And well, that's it. You can find the slides on the first link, and here are all the references that I used for to make this presentation. I really encourage you to like take a look at the CPython 3.6 code. Like, even though it's C, it might seem hard to understand at first glance, but really, like, it's really well documented and like really easy to read. So just give it a look. Thanks for listening. And I also want to thank all the FOSDEM staff for organizing everything. So